Learning Outcome 2, Functions and Algebra, 12.2.7. A. Investigate and use instantaneous rate of change of a variable when interpreting models of situations. Welcome to another lesson in our series on calculus. I hope that through this series, you have gained both an understanding of the power of calculus as well as some appreciation of the achievement that the invention of calculus represents in the recent history of mathematics. Magava is back with us again. Hello, Magava.
Hi there, everyone.
So far, we have interpreted the derivative as the gradient of the tangent to a function or graph at some point on that graph. Today we're going to expand our understanding of the derivative to include the concept rate of change, something that will hopefully make sense as we progress through the lesson. By the end of this lesson, you should be able to interpret the derivative as the measure of the rate of change of a function. Today I have some really fun animations for us to look at. I'm hoping they will help us to develop an understanding of the concept of rate of change.
Cool. I'm ready to help wherever I can.
I'm glad to hear that. Let's get started. What I have here is the graph of a cubic function.
Right. Just like the one we drew in our previous lesson.
If you notice, there is a little bicycle standing on the graph. What I would like you to do is to watch how the bicycle rides along the graph. Here goes.
Hey, that is pretty cute.
Glad you like it.
But how did you do that?
I'll show you later on. Now I'm going to let the bicycle ride along the graph again. While you're watching the animation, I want you to tell me only whether the bicycle is going uphill or downhill.
Seems straightforward to me. Let the race begin. All right. The bicycle starts off going uphill. It is still going uphill. And now the bicycle is going downhill. It is still going downhill. Okay, the bicycle is going uphill again. It is still going uphill.
As you said, that was easy enough. We're going to watch the animation again. Now, I want you to try and focus on something else. I'd like you to think about why the bicycle is going uphill or downhill in terms of what is happening to the function. In particular, what is happening to the function's value.
Okay. Let's try that. It seems to me that the bicycle is going uphill because the graph is going up. The function value is increasing. Look, the y of the function value is about 2. And now it seems to be about 12. The function value seems to be increasing as the bicycle is riding along. How am I doing?
You're doing great. Let's carry on. What's happening now?
The bicycle is definitely going downhill. And it seems to me that it's doing this because the function value at the y value of the point on the graph is decreasing as the point moves from left to right.
We'll stop there for a second because that's an important idea that you just identified. And I want to discuss it for a bit. We talk about functions as increasing or decreasing, or as constant if they neither increase nor decrease. I have drawn these three cases here. The first sketch represents a situation in which the function value is decreasing. I want you to notice that the function value, or the y value of the points on the line, gets smaller as I move from left to right.
Okay, but if we go back to the bicycle, if I turn the bicycle around, I'll be riding uphill. And wouldn't we consider the function to be increasing then?
Good point, MacGyver. What we do to avoid any possible confusion is to adopt a convention. In this case, we would say that the function value decreases as the x value increases. In other words, as we go from left to right along the graph. Now have a look at this sketch. Can you describe this function?
Sure. I would say that the function value is increasing because as we go from left to right, it's getting greater.
Quite correct. What about this one?
As we go from left to right, the function value stays the same. Could we say that the function value is fixed?
Yes, we definitely could. Though we tend to say that the function value is constant. Let's go back to the animation again. This time, I'd like you to use the words increasing and decreasing to describe what is happening to the function value.
Ready? At this stage, the function value is increasing. It is still increasing. Now the function value is decreasing. It is still decreasing. Okay, now the function value is increasing again.
Good. Now, just to be sure that all of that makes sense, let's try it one more time with a different function. While you watch, please, would you describe what is happening to the function value?
Let's go. In the beginning, the bicycle is going downhill. So the function value is decreasing. It is getting smaller as x increases. Now the bicycle is going uphill, and the function value is increasing. It is getting larger as x increases. And now the bicycle is going downhill again, and the function value is decreasing. It is getting smaller as x increases.
That was great. Thanks, MacGyver. Whether or not functions increase or decrease is an important property of functions to consider. Now, I would like to link this property to our work on derivatives. Have a look at this graph. Please won't you draw a tangent to the graph anywhere in this region where we decided that the function value was decreasing as the value of x increased.
Like this.
And what do you notice about the gradient of that tangent? In other words, is it positive or negative?
It's negative, isn't it?
Quite right. Now, please draw a tangent to the graph anywhere in this region where we decided that the function value was increasing as the value of x increased.
Okay, it would be like this.
And what do you notice about the gradient of that tangent? Is it positive or negative?
It's positive, isn't it?
It sure is. And did you notice a pattern?
Not really.
That's okay. Let me show you then. Well, when the function value decreases, the gradient of the tangent is negative. When the function value increases, the gradient of the tangent is positive. And since the gradient of the tangent is given by the derivative can help us predict when the function will be increasing and decreasing. For instance, here in this region where we decided that the function value was decreasing as the value of x increased, the tangent will have a negative gradient, and so we would expect the derivative to have negative values for the x values in this region.
So what you are saying is, when the gradient is positive, the function value is increasing, and we could expect the derivative to have positive values in that region. And when the gradient is negative, the function is decreasing, and we could expect the derivative to have negative values in that region.
Well put, MacGyver. Now, I want to go back to the discussion of the bicycle because I think that our discussion of what was happening was pretty limited.
What do you mean?
I think it would be easier to explain if we go back to the first animation. Ready?
Yep. Go for it.
Up until the point where the function turns, the function is clearly increasing. But in this first half, the function seems to be increasing more quickly than in this second half. The function is not as steep. Having passed the turning point, the function starts decreasing. But notice it does this slowly at first, then does so quite a bit more quickly, and then it seems to slow down again. Does that make sense?
Yeah, it does make sense. But isn't this what you were talking about earlier when we said we're going to be looking at rate of change in today's lesson?
Glad to see you've been paying attention. Rate of change is a very important aspect of functions. What we've seen in our animation is that not only is the function increasing, but the rate at which it does so changes. Mathematicians call this the rate of change of the function. Let's take a closer look at this concept. I want to describe it a bit more precisely. Here I have an enlarged portion of that function we've been working with. I'm going to work off this copy of the diagram. I'm going to break this part of the bicycle's journey into two parts. First, we're going to consider the interval from when the function crosses the x-axis at -2 till -1,5. The x value has increased by half a unit, so the function value has increased by approximately 12.5 units. Now, let's look at the second part. As the x value increases by another half a unit, so the function value increases by approximately 7.5 units. The function value has increased by less for the same increase in the x value. We say that the average rate of change is less over the second interval than over the first.
That makes sense, but there are two things I'm worried about.
What are they?
First, what you have there is the change in y and the change in x, which is what we usually use to determine the gradient.
Absolutely. If we drew these lines, the change in y and the change in x for each section would give the gradient of these lines.
And since the gradient for the second section is less than for the first, and what you have called the average rate of change for the second section is less than for the first, can we say then that the gradient and the average rate of change are related?
That is exactly the case. What was the other thing that was bothering you?
There are two things. Although we've said that the average rate of change over this second interval is less than for the first, it actually changes in this interval as well.
Can you show me what you mean?
Actually, I'm one step ahead of you. I've already enlarged the second interval from your drawing so that I can show you more clearly what I mean.
I'm impressed.
If I divide this into two equal horizontal changes, then once again, the vertical change in the second part is less than the vertical change in the first part. And the gradient for the first part is steeper than for the second. But there is more than that if I compare it to your first part. But more than that, the gradient for the first part is greater than your gradient, and the gradient for the second part is less than your gradient.
So, what you're trying to point out is that the rate of change of the function is changing all the time.
And if we made the interval smaller and smaller, then the average rate of change would more accurately represent the rate of change at the point in the interval.
Yes.
And if we kept on forever letting that horizontal change get closer and closer to zero, we'd end up with the tangent. So the gradient of the tangent gives us the rate of change at the point.
And we call the gradient of the tangent
the derivative.
Or more accurately, the instantaneous rate of change at a point. Good work. Now I want to look at something else. We're going to go back to the animation we were working with before. This time, let us see what happens to the gradient of the tangent. Ready?
Ready.
In this first stage, the function value is increasing and the gradient of the tangent is positive. However, the gradient of the tangent is becoming less and less steep. In the next stage, the function value is decreasing and the gradient of the tangent is negative. However, the gradient of the tangent becomes more and more steep, then less and less steep. The last part, the function value is once again increasing and the gradient of the tangent is positive. And notice how the gradient of the tangent is increasing all the time. Let's go back to that table that we studied together earlier on. I have added a column on the left that captures the essence of what you were saying as you watched the last animation. Would you like to draw the shape of the graph that corresponds to each cell?
Let me try.
Good work, MacGyver. Do you remember in the lesson where we drew the graph of the cubic function?
Yes, of course.
And do you remember what I suggested you write? Instead of writing turning point, when you started calculating the values of what turned out to be the turning point.
You said we should call them stationary points.
Correct. Now I'm going to show you why. Notice how the gradient of the tangent is negative, but how it is becoming less and less steep now that the bicycle goes past the turning point, and the gradient of the tangent becomes positive. What does that mean about the gradient of the tangent at the turning point?
We already know that from work we've done in other lessons. The gradient of the tangent is 0 at the turning point.
In other words, for just a moment, the rate of change was 0. If you like, there was no rate of change. So we can say that the rate of change was stationary. It did not change.
Sure, but why the fuss? That was the turning point.
So it was, but look at this cubic function. Notice how the gradient of the tangent is positive and how it becomes less and less steep. Then here in the middle, the gradient is 0 for an instant. And after that, the gradient of the tangent is again positive and becomes steeper and steeper. There are graphs that have points at which the gradient of the tangent is 0, but the graph does not turn. The point at which the derivative is 0 is a point of inflection, not a turning point. So until we know whether the graph turns or not, it is safer to refer to the points where the gradient function is 0 as stationary points. Let me show you the graph of one last cubic function. Notice how the gradient of the tangent is negative throughout, and notice also how it changes and yet it is never 0. The point at which the gradient changes from getting less steep to getting steeper is also called the point of inflection.
There is so much to this topic, isn't there?
Yes, and there really is. In fact, there are mathematicians who devote their whole lives to the study of calculus.
That's incredible. I wouldn't have thought there was enough to discover about one topic.
And there's a whole lot more to calculus that we don't study at school level. But I think we have more than enough to remember, especially for one day. So let's recap what we have discovered in this lesson. In this lesson, we looked at the rate of change of functions. We found that when the derivative of a function is positive, the function value increases as x increases when the derivative is negative. The function value decreases as x increases, and when the derivative is 0, the function value is momentarily neither increasing nor decreasing. It is stationary. A curve can have a positive gradient which is getting steeper, a positive gradient which is constant, a positive gradient which is getting less steep, a zero gradient at stationary points, a negative gradient which is getting steeper, a negative gradient which is constant, and a negative gradient which is getting less steep. Stationary points can be turning points when the function changes from increasing to decreasing, or from decreasing to increasing. Stationary points can also be points of inflection where the gradient remains positive or remains negative. But changes from getting steeper to getting less steeper, or from getting less steep to getting steeper. There can also be points of inflection and points where the gradient of the curve is not 0, but there is a change from getting steeper to getting less steep, or from getting less steep to getting steeper. And now it's time for you to do some work on your own. I'd like you to consider the graph and, using the words increasing and decreasing and constant, describe what is happening to the function value in the interval a,b, in the interval de, at a, b, c, d, and e. Determine which of the marked points where the function value is increasing. It is increasing most, and at which of the points where the function value is decreasing, it is decreasing most. See you next time.